won't speak about cracks or fracture, but just about something else. But this method might be applied also for crack problems. So, first of all, who am I? So I'm a third-year PhD student, and in the last 3 years, I've been working on. So just before my PhD, I worked. I was interested in how we can perform dynamic measurements using 3D printed strain sensors. And then at the beginning of my PhD, I just switched topics. And then the first part of my PhD is about studying lattices, so lattice structures. And here just a figure from a recent submitted paper where we study with my supervisor, Professor Giulio Greer, the fracture of microlattices. And then the second part of my PhD is about using machine learning, specifically deep learning, for studying architectural materials. In this case, we studied interlocking materials. And then more recently, I've been intensively working on how we can predict physical fields like deformation, stress strain fields in materials and structures using graph neural networks. So first of all, I would like to give you a global view of where this work is framed. So basically, all of you know that additive manufacturing plays a vital role, and in the recent 15 years additive manufacturing grew a lot, and it allows us to architect materials at different scales. This is an example of microlattice at a micro scale, and then the design space will be larger and larger. So if we want to find optimal architectures for our materials, so we can exploit the large amount of data that we can create, and we can gain knowledge from data-driven approaches. In this case, I've used deep learning. So the focus of this work is the following. So given a target property, for example, you want to have a structure which is compliant along one direction and is different on the other, or you want to maximize the fracture toughness. So you want to find the optimal architectures which satisfy this condition, this requirement, and this is called inverse design. So in this case, we want to maximize bandwidth strength, defined as the maximum of the macroscopic effective stress strain curves. And we obtain some design candidates, which will be later simulated and tested. So, and this is the reason we are talking about inverse design of lattice materials. Well, the first part is about non-uniformly assembled architectures. So, despite the fancy name, so now I'm showing you what it is about, actually. So, we're using a bottom-up approach. So, instead of starting from a pre-existing structure, for example, you might start from a lattice material, just a triangular lattice, and you might change the local property to tune some other properties, like you want the macroscopic stiffness to be along one direction, one specific value. In this case, we start from a simple building block for simplicity with one node per edge, and then we connect each node to the others without leaving unconnected any node. And we obtain 8 building blocks, base building blocks, plus their symmetries, so reflections and rotations. And so these are beam-based building blocks with, so we have a thickness Ti, a length Li of each beam. So, and if you combine these building blocks together, you obtain more complex geometries, and then we call it n by n unit cells. You can tessellate these square building blocks, obtaining different, more complex architectures. So this is the reason why it's called non-uniform design, since we don't have a uniform, just one unit cell which is tessellated, but we have more building blocks combined together to generate more complex patterns. So if you consider one basic design, you consider this as a unit, just this is a uniform design, and you simulate it considering post-buckling. So you tessellate an infinite plane, and then you perform post-buckling simulations. This is the post-buckling shape. You can notice some long wave phenomena along the 45 directions. While if you consider the same building block combined with its 90 degrees rotated version, you obtain more complex pattern, and the effect of this long wave phenomena is somehow eliminated, and this is confirmed by just looking at the buckling strength as a function of the loading angle. So we are here compressing these structures, and they're going to buckle. And so for different loading direction, we obtain these curves. And if you consider different tessellation numbers, like you can say 1 unit cell, 3 by 3, and 10 by 10, consider periodic boundary conditions. So you obtain a decreasing performance in the basic design, the blue curves. You see that buckling strength decreases, while for the non-uniform design, it remains invariant with the loading direction. So our goal is to inverse design, so we have to create data sets before. We start from the basic building blocks, and then evaluating the buckling strength by simulations along different loading directions for each building block. We can choose which building blocks to combine. Of course, this is an arbitrary choice. So in our case, what we do is we combine together these two previous building blocks that I've already shown, and we create more complex unit cells. So we benchmark our results with a recent result on sponge-inspired designs, where in a recent paper they show that this design is one of the best in terms of buckling strength. So, and we randomly extract 2,000 geometries from the whole 4x4 unit cell design space, and we show here that about 40% of the geometries inside the dataset outperforms the sponge A. Let's call it sponge A for simplicity, which is this one. So, and the second part is, so since we want to inverse design, we need a tool to quickly predict the buckling resistance of our architectures. So therefore, what we do is we start from a lattice architecture, compressed along a loading direction theta, and then we create an input, we create a matrix representation based on the number of building blocks we have. So here we have two building blocks types, therefore we have a binary matrix, so for example 1 and 2, and then we vectorize it to concatenate the loading angle, and then we train a deep neural network and optimize the hyperparameters to predict the function, which is the buckling strength as a function of the loading angle. So and here are some performance of the network, so we don't have time, but if you're interested we can go into details. And the first step is find out the inverse design, so finding optimal architectures. So what we do is basically we have our dataset composed of architectures with the corresponding buckling strength vector for different loading directions. And then we start with a random initial population, and using a genetic algorithm here, so we don't have time here for the details, but what it does is optimization algorithm which provides you some new design candidates, some new architectures, whose property, which is the buckling strength in this case, but it might be also, for example, fracture toughness or whatever you want. So I can predict it by the previously trained deep neural network. And so after some runs, so we select the 6 best design candidates. These are unit cells. And then here we can show that, of course, we show that this method discovers actually lattices that with superior performance compared to the data set which was in the for training and testing the network. So here are some patterns that we show that we have some 45 degrees periodic patterns. And then, so we want to evaluate the performance of the best design candidate at 0 degrees, and we compare it with the sponge designs. So from the stress strain curve here, we can show the stress strain curve. We see that the red curve is our architecture, outperforms the sponge designs in terms of maximum stress, and so here just a summary plot of the buckling strength along for different loading directions. Of course, the stiffness of the two sponge designs is not, for some angles, it's larger. So here there is a discussion about this deep sea glass sponge, which has the stiffness along the vertical and horizontal direction for evolutional purposes. And then finally, we want to, since in real applications we have finite size structures, so we want to test the high-performing lattices that we found. First of all, so we create finite size structure of our architecture, the red one, compared to the two sponge designs. So as you can see here, these are the post-buckle shape after the post-buckling simulation, And you can see that for our geometry, the buckling is triggered from the boundaries. While for the two sponge designs, so we have a more uniform deformed shape. And this is reflected by the stress strain curve. So of course, this means since our architecture is not symmetric, the boundary effects dominate buckling in this case. And so we ask ourselves if our results might be better for a symmetric version. So what we did is we took the initial unit cell, and then we create the symmetric version just by taking the unit cell and reflecting by the vertical and horizontal axis. And then we tessellate a 2x2 tessellation, considering a frame around it to have a fine size structure. And finally, what we did is so we 3D printed using stereolithography different samples for our architecture, the red and the blue, for two different loading directions, the 0 and 90 degrees, since it doesn't have symmetry along the 45 directions, and samples for the sponge B. And here we have some snapshots of the before the compression load and before failure. So looking at the side lines, the red and the blue, which are the stress strain, macroscopic stress strain curves, you can notice that our architectures actually in average outperform the sponge design, the yellow curves. However, there is a larger scatter for these curves for our architectures, and this is due to the fact, as you maybe it's small here to see, but so the displacement of the structures is not visible compared to the sponge B, which means that being optimized for buckling, so they are less prone to buckle than the sponge design. So therefore, their effective buckling strength is almost the same as the effective fracture strength. And then we compare with other classical designs using simulations, and we have a gain of about 15% and between 30 and 90% of buckling strength compared to the sponge B design and traditional grid-like designs used in infrastructures and classical applications. So of course we have some limitations. So we have, if you want to tessellate not square building blocks but different, for example, hexagonal, matching the boundary nodes might be somehow challenging in 3D especially. And then, of course, the initial choice of how many building blocks you choose. In our case, we chose just 2 building blocks, and what's the criteria to choose them is somewhat arbitrary. And of course, if you choose, so the more building blocks you choose, and the larger design space you have, and the training data to train the network to predict the property will grow. And then finally, if you want to control, if you want to have, for example, lattice structures with spatially graded properties, this might be cumbersome because you might want to have smaller building blocks in some parts of the structure. But some key takeaway is that so with this method we can design more complex architecture just by combining single basic building blocks, and then using just a deep neural network as a decider and a genetic algorithm to search in the design space of the possible architectures. And then our method can control topological features, so which are how many nodes you have, which beams are connected to each other, what's the connectivity, while other methods cannot, just by controlling those of the single building blocks. So finally, thanks to my supervisors, Professor Chao, NTNU, Julia Greer, Caltech, and my main supervisor, Filippo, Berto. That is me. So if you're interested, just send me emails or LinkedIn. So thank you.
Thank you very much. So we still have time for questions, unless anyone is sorry to go lunch. Yeah.
You optimized your structure for buckling strength.
Yeah, exactly.
Did you have looked into how other properties are affected, like stiffness or whatever? Because you have really optimized it for buckling, so...
Exactly, yeah, we looked at other properties, but so this method is a kind of general method, so you can apply to stiffness, to...
Yeah, but you have only made it for buckling.
Exactly,
so you could have compromised some other parameters seriously.
Yeah, for example, as I said before, as you remember, so now it's far away. But if you remember the certain course for compare our architecture with the sponge designs. So for example, for some loading direction, the sponge designs are better. For example, for the vertical and horizontal directions, and that's we argue that is due to an evolutional reason, because so if you're interested, so the sponge basically at the beginning of in the early life has this these vertical and horizontal struts which are not connected, and then when it grows they attach together, so it needs support at the beginning of its life to and then that's the reason it's stiffer. So but of course next steps of this work are applying multi-objective optimization. Like we want to optimize different properties.
Yep.
Right.
Okay, good. Okay.
Michael, did you get to characterize the Poisson of these structures?
You get
To measure, to characterize the Poisson?
the Poisson,
Yeah.
Poisson's ratio?
Yes.
No, actually, no.
Which should be interesting.
Yeah, actually, yes. Yeah. I noticed that, so I've been working a while on this, so I haven't shown everything, but so there are, so you have the possibility to create, for example, auxetic structures, so with negative Poisson's ratio, so it's, the design space, as I said, is really large, so if you combine many different building blocks, you could obtain really everything you want. So, and this is just in 2D. So if you want to do in 3D, of course, the design space will be larger.
Thank you.
Yeah, thank you.
So thank you again. And this
Thank you,
comes to the end of our session today. This is one presentation from Dr. Sherman. And